sorry, try to enter back now. Ada Hanifah Hana kena remove. Okay. Okay, Assalamualaikum warahmatullahi wabarakatuh. And Izham also. Okay. Okay, Assalamualaikum warahmatullahi wabarakatuh and a very good afternoon. Sorry, okay. We have a few delays here. Okay. Today, okay, better off the WhatsApp. Okay. Okay, so today we will talk about the measurement of flow and volume of blood. So first of all, everything, anything before what I call for a start. Okay. For a start, you need to know the motivation. Okay. Why people are interested. I know in terms of research, okay, this is very good because that's why I like to not imitate lah kan, but last time I was taught by Prof Nasir. He's from UiTM. Last 2 years he was the dean of engineering, electrical engineering faculty of UiTM. It has been sometimes he became the the dean of electrical engineering. I think like 10 years or 12 years in UiTM. Okay, he always come to the class and he told us about what's the difference between the mathematician, physicist and engineer and engineer. Okay, there's a lot of things, but I don't want to go to that. Okay, I should tell you any jokes before the class. Okay, so for the physicists, they study, they do the work. Okay, they have one motivation to understand how the universe works. Okay, macam mana alam ini berfungsi. Okay, that's how physicists. So they investigate. Okay, about let's say blood flow. Okay, what is the is there any current in the blood flow? Something like that. Okay, are there any voltage? Okay, so for physicists, okay, how much is the so how much the pressure, everything. So but for us engineer, okay, we have what another motivation. What is the motivation? We want to solve a problem. Okay, we want to solve a problem. That's why although we learn the basic of engineering, okay, comes from physics. Okay, all this F equals to ma and so on. Okay, if you look at PV&LT, all those equations, okay, it's a physics equation. It's a physics equation. But the difference between the physicists and engineers, okay, we solve problems. Okay, this is what Dr. Cheng told me because he's a physicist. He's actually have a physics background. Okay, applied physics background. Okay, he said that we study anything. Okay, whether whether honey has a impedance or not, whether directly or not. Okay, so but what does it contribute? You cannot answer us. Okay, but for us, okay, if you study something, if you do something, okay, it should solve something. So okay, coming back to our our lecture today. Okay, so why you want to study the flow, okay, and the flow and the volume of blood. Okay, maybe okay, if in our case, maybe we would like to know that if there's a clotting, okay, obstruction in the blood vessel. So this will justify if you want to, for instance, have a what we call a bypass, okay, bypass of the artery and so on. So that's why you need a motivation. Okay, why you are studying this? That's why some of you complain about like last time about thermofluids and so on. Okay, you all complain pasal penama ni thermofluid, apa ni kita bioengineer, biomedical electronic, apa pasal guna belajar ni. So it's the same here. Okay, you need okay, you need we design this course. Okay, there's a reason. Okay, bukan saja there's a reason. So okay, this is just motivation lah. The global blood flow measurement device market. Okay, I know it's small, but you can see in your, if you download your lecture now. Okay, it can be up to 575 million Is it? Lebih kurang lah. I cannot see the. Okay, I don't see the. Okay. Oh, sorry. They 371 million in 2016, but 879 million by 2025. Okay, so that's how much it worth. Banyak okay, a lot. Okay, oh makin ramai makin keluar ni apa cerita. Okay, okay. So so that's the amount of value because okay, there's a lot of because people. That's what I told you in the past, and I think you also know about this. Okay, apa nama ni? There's increasing demand. Okay, biomedical engineering. Okay, medical doctors, nurses, and so on. There's the demand for this work. Okay, the jobs. Okay, and job market and the problems. Okay, that is going to be solved by this profession is increasing because the numbers of people are increasing. Okay, so these are the this is for the tips for those in the apa nama ni in the class lah. Okay, so we have a few type of measurements. Okay, that we want to solve. Okay, for blood flow. You want to the first thing is the concentration of oxygen and also other nutrients in cells. So if you can relate what we have during this COVID, okay, it's much more critical. Okay, because you want to see, okay, because like for instance COVID, okay, we have problem about the oxygen, the amount of oxygen in our, that's why SpO2. Okay, although we are not talking about SpO2 per se in this lecture, but we try to understand, okay, what is it is one of the parameter that we are going to measure. Okay, during this COVID, okay, you use SpO2, okay, the to measure your amount of oxygen. If your blood has less than 95% of oxygen there, okay, the reading is lesser than 95%, you should go to the doctor. Okay, so okay, and then the second class measurement is a blood flow and changes in blood volume. Okay, and then we want to correlate to the concentration of the nutrient. The third class, okay, measurement blood flows, okay, which correlates adequately to blood pressure. Okay, and then the fourth class ECG, which is also correlates to the blood pressure. So these are the things that why we want to do this blood flow measurements. Okay, concentration of the oxygen. Okay, the blood volume. Okay, because of the concentration of nutrients. Okay, the blood the what we call to relate to know the relation between the blood flow and also the blood pressure and also the ECG relation between the ECG and also the blood pressure. Okay, so far so good, I hope. Okay, so there are few ways, okay, of doing your blood flow measurement. Oops, it's still there. Okay, ada. Okay, so we want to measure the flow average over a number of heartbeats. So this is one of the methods. So, okay, in this lecture notes, we have a few formulas. I hope you can remember. You can what we call some. It is usually simple equation. Okay, but you need to practice. You need to and then try to find the logic. Find the logic between the relation between this. Okay, so I hope you won't get scared. Jangan takut. Don't get scared with the equation. Okay, try to think. Okay, the logic of it, because those people who create this equation, okay, they are not. I know some people say, okay lah, memang mereka menyusahkan lah your life now. Okay, but the reason they do it because they want to help people. They want to assist people. So this is the easiest way. They will simplify it, okay, to make sure that people can measure, okay, the parameters. Okay, for instance, C apply to C. Okay, the concentration. Okay, usually you need to have the assumption. Okay, uh, you need to have assumption. I know maybe in your real life, okay, you you may not get 100% the same. Okay, I know during Asasi when I do the experiment sometimes the graph is so far sometimes it's different. Okay, but this we call the the nature's law. Okay, the nature's law. Okay, usually we will get this much. If without the nature's law, we are susah lah, banyak benda tak boleh lah. You cannot get your laptop, you cannot get your apa nama ni, your battery, okay? You punya battery handphone semua tak dapat lah kan. Semua whatever we have now kan, okay? So let's look at this, okay? C. What is C? C is the concentration, okay? So this is the okay. So the M naught, okay? So the M naught is an indicator, okay, added to a volume V. So, okay, C concentration equals to this M naught, okay, divided by V. M naught, okay, given quantity. Okay, so if you study your chemistry and so on, so this is one of the idea, okay, how you want to measure your concentration. Okay, so if then you add this quantity of the indicator, okay, so there must be a difference of concentration. So I hope, okay, we go to basic again. Okay, we use this symbol, okay, to define to depict the difference of the concentration. Okay, because there's now an incremental. Okay, there's increment penambahan. There's an addition of. Okay, there's more. Okay, there's more concentration there. So delta C equals to, okay, the quantity of the increment of the M divided by the volume. Okay, and V is sama, V is sama because you don't add anything. Okay, the V, okay, then the normal V is the same. This is the indicator that we add up. Okay, fluid volume in the measured space is continuously moved and replaced in the flowing stream to maintain fixed change in the concentration. Look at this. Okay, a continuously fixed quantity of indicator is added per time. Okay, so you can see that. Okay, so we want to know, okay, flow. So what is the difference of flow? V, volume kan. Okay, volume. Okay, divide. Okay, the dV dt. Okay, the changes in the volume and the changes in the time. Okay. Just want to relate. Okay, this is more beautiful when you have problem. Okay, week ago I have a problem of apa nama ni, bekalan air. Okay, the water supply. Okay, is being what I call affected by they are cleaning the logi English macam apa water tank, not water tank lah kan. Okay, for even I think your asrama, your hostel also being affected. Okay, so there's a problem of water supply. Okay, to cut it short. Okay, now it's 1 minute to 4. Okay, so we have a my house. Okay, we have problem about the water supply only comes from the direct water. We don't have the supply from the tank. Okay, the other. Okay, so you can see that. Okay, the water flow is slow. Okay, we have a supply. Okay, we have a direct water supply, but it's very slow. So at that time I start to think, okay, we want to fill in your baldi, your pail. Okay, your pail with water. So I have been thinking, okay, how about if I take a stopwatch, okay, then I know how much of the volume and start to measure it. So this is the same with it. Okay, Okay, people want to solve the problem by looking at this DVDT. DVDT is the difference in the volume and also the difference, the changes in the time. Okay, so if look at this, uh, okay. Now let's say in terms of flow, so dm by time, and then the changes in the concentration. So maybe you want to measure the difference of the volume. Maybe you don't have the information, but then you know the indicator, the quantity of the indicator, and also the time, and also the incremental in the concentration. So if you have this information, you may know the flow. Okay. Why is this this is important? This is important because this is important because when you want to measure your blood flow, maybe you cannot drain out your blood lah. But you can measure the indicator and also the concentration. One thing that information yang that is important here also, this is invasive. Invasive. We will go to non-invasive, but later. Even for the async, async lecture we will do on the ultrasonic. Another one is plethysmograph. Plethysmography, and also ultrasonic. Both of these are non-invasive. This is invasive. We will see why I said invasive. So here we use the Fick technique. Technique Fick. Sometimes here you can see that it also the DMDT. DMDT, which is the indicator on the time, and now we have the arterial concentration of the oxygen and venous concentration of the oxygen. So F is the blood flow, and then the DMDT is concentration of the O2. So now you know how much is the consumption of the O2. Now you need to know only the arterial concentration of the O2 and the venous concentration of the O2. Kurang ni, I don't know why. Hope that your friend can masuk kelas. So the measurements, how does it measure? The blood returning to the heart from the upper half of the body has different concentration of O2 from the blood returning from the lower half. Blood returning to the heart from the upper half of the body has different concentration of O2 from the blood returning from the lower half. So this is the assumption that that they make. If not, how can they measure it? So we have another 15 slides. This. So this is how does it work? This is how does it work? Similar methods of measuring cardiac output. That's why the first thing, if you see this, tengok ni, you know this is invasive. Invasive. So invasive, but although we always talk about non-invasive, but sometimes you need to do invasive invasive measurement. That's why I'm not saying that blood glucose is entirely invasive, but people have been trying. I think I told you before we try to make a biosensor based on the saliva, based on the infrared. Even now, but this now it is acceptable, but still, it is acceptable, to use the infrared thermometer. But still, if you want the accurate measurement of temperature, you need to have your measurement, okay, on your skin. Even sometimes they poke it in your mouth, okay, or on the other side, okay, to measure, okay, to make it accurate. So this is the same. Sometimes you need, pick 10 millimeter. I need to make it a bit smaller. Okay. Hope you can see, better. Okay. So you have the arterial sampling here. Okay. You have the venous sampling here. Okay. So this is very invasive, and then you chuck in the spirometer, okay, for oxygen, to measure the oxygen. Okay. The 7 methods of measuring cardiac output. I hope you are not lost. The hukum fig is equal to just now. Okay. This F. Okay. F overflow, and then you have your the DMDT, okay, and then divided by the concentration of your oxygen, the arterial concentration of O2, and then the venous concentration of oxygen. Okay, I hope you are not lost. Okay, okay. So in the Fick method, the indicator is O2, consumption is measured by a spirometer. Okay, the arterial venous concentration difference is measured by drawing. Bukan lukis, drawing is take samples through catheters. Okay, there's a catheters placed in an artery, one artery. Okay, and in the pulmonary artery. Pulmonary, what is pulmonary? I hope you still remember our lung. Okay, in the dye dilution method, dye is injected into the pulmonary, okay, artery. Okay, and samples are taken from the artery. Okay, just imagine you inject there, okay, and samples are taken from the artery. In the thermodilution method, cold saline is injected into the right atrium, and temperature is measured in pulmonary artery. So this is the way how people use this Fick technique to measure what I call the cardiac output. Okay, so remember this figure. Okay, this is practice here. Okay, as shown in the figure here. Okay, the oxygen concentration is measured by using a spirometer is 300 milliliter per minute. Okay, the oxygen concentration measured by using a blood gas machine is 0.24 ml per ml. Okay, liters per liter. Okay, if you remember. Okay, on the previous slides. Okay, in the arterial blood. Okay, and 0.18 milliliter per milliliter in the venous blood. So this is logical because why? Venous blood, okay, is sure have less oxygen. Okay, so 0.6, 0.06, I'm sorry, 0.06 have been consumed. There's a difference there. Okay, so the cardiac output will be Q. Okay, and then this is the equation. Okay, this is the equation, and this is the answer. Okay, you have a 5 liter per minute. Okay, so this is the cardiac output is 5 liter per minute. It's a lot, Okay. So about the indicator, okay, in dilution method, okay, it uses rapid injection. So there's a continuous injection, okay, and then the bolus. Bolus is that, if you still remember when you learn the biology, is a bit by bit lah, it's a bit by bit lah, okay. It's a bit by bit, but it's rapidly injected into the vessel, and the variation in downstream concentration of the indicator versus time is measured, okay, until the bolus has passed. Okay, I hope you still remember the when you study your biology or your anatomy and physiology about when you're eating, okay, your food, okay, your food being swallowed, okay, it is in the form of bolus. Bit by bit lah, chunk by chunk, start to think, okay, macam bola lah, okay, like a ball, okay, okay, it is not like air terjun, it's not like apa nama ni, it's not like waterfall, okay, you eat bobo, you eat your porridge, your bobo lambuk, everything goes down. Everything goes down. Okay. So it is by bolus. Okay. Even if let's say in your what call other part of your body sometimes, okay, it is by bolus. So okay. So the quantity of indicator DM contained in DV. Okay. Again, this is the DM. Okay. Quantity of the indicator DV. Okay. DV is something to do with the volume. Okay. Is the concentration of okay. Concentration C. I have C is okay. Be careful about this C because C can be okay. EMC square can be light. Okay, C can be Coulomb. C can be okay. So please understand. This here C is a concentration. Okay. So okay. So dm equals to this concentration. Okay. But it has the okay. It is being subjected to time. That's right. Like in the physics, okay, okay. So this variable, okay, being subjected to something, okay, whether it's by time, by pressure, okay. So if you start to think back to your form 4, form 5, especially your form 4, okay, that's why most of the time you start to appreciate that, okay. People you always have this okay you learn about your differentiation your apa nama ni differentiation pengambilan apa lupa dah pengambilan okay uh, we use always to time okay it's always to time lupa dah what is panggil dia okay tak apa okay dvdt okay equals to okay so we change it back to dvdt okay ct to dv why okay because we want to get the dvdt okay so we have this flow fi okay instantaneous flow because it's why instantaneous because something to do with your bolus okay okay it's dvdt therefore dm okay dm because dm equals to fi okay ct dt okay because we have insert this into the equation okay there's a beauty of it lah after this so we want to relate it to this equation we want to relate to this equation so now you want to what column tadi differentiate then not invert apa nama lah lupa dah I forgot already please write in the chat lupa dah I bila nak tulis bila nak cakap baru lupa integrate sorry integrate okay you want to integrate okay so now okay you know the dm okay just now you want to measure changes but now you want to measure how much indicator that you want okay so you integrate this flow and also the concentration this flow and concentration so m okay m okay and suddenly you say okay why f is not f I know some of you have this answer already especially those who are very good in maths but okay sometimes we tend to forget okay this is constants okay so we take it out okay so ct okay because it is time it is okay it is influenced by the time okay subjected to time so this one okay the concentration that can be this ct dt that can be integrated okay so you can measure the flow okay with the condition that you know okay the m okay so you have your m okay then okay so the amount of the okay the difference of the concentration that you have measured then you have your Q. Okay, now there's another way of what we call there's another way. Okay, you want to measure the flow. Okay, whereas the Q is the heat content of the indicator, and then the rho B is the density of the blood. Okay, Cv is the specific heat of the blood. Okay, T is the temperature. So this is maybe okay. This will have, although I know in terms of equation this is more headache than this lah, but okay, but okay, in the practical world, okay, maybe this is better. Okay, so this is the rapid injection indicator variation curve. Okay, so you can see that, okay, bolus injected at time A. Okay, there's a transportation delay because the concentration. Okay, because you inject the your indicator. Okay, and it will be moving. Okay, like a bolus, like I told you. You have to imagine that. Okay, you're eating something and then your food is going to the stomach. Okay, it's something like that. Okay. Okay. So the concentration begins to rise at the B. Okay. After the peak, okay, here is the peak, is passed, the curve enters the exponential decay region between C and D. Okay, so it starts to go down, which will continue decaying, okay, to T1, okay, T1 is here is T1. There's no recirculation, okay, everything goes into the blood, okay, into the vessel, okay. Recirculation may cause a second peak at the E, before the indicator becomes really mixed in the blood at F. Okay, may, okay. The dash curve indicates the rapid acceleration that occurs where there's a hole between the left and right side of the heart. Okay. So they have simulated this. Okay, they have done the experiment. They have looked also. Okay, this is the why it becomes like this. Okay, why it becomes like this. Okay. So there's two things here. Okay, about the equation. I hope you can watch again and again this video. Because I'm recording it. Okay. And also try to relate these two. I know if you look at this and then the equation, jadi susah kan? Okay. Okay, let's go to the here. Okay, I make it fast lah. Yang reading ni I make it fast lebih for you lah, because we try to get 430 or slightly 435 lah. Okay, so the dye. Okay, what are the materials? I know I'm a biomaterial guys. When I look at this, mata I cerah sikit lah kan. Okay, so the dye dilution, okay, what are the, it's usually colored. What are the type of material that you are going to use, okay? So this is indocyanine green, okay, cardio green. Maybe it is easy for us to see. Okay, it is easy for us to see what is the color, okay? This the indicator. So this is other what we call the characteristics of the indicator that you should use. Okay, inert, okay, no reactions, harmless, definitely. Okay, you can measure it easily. Okay, economic means cheap. Okay, not cost a lot. Intravascular. Okay, intravascular means that it is you can contain it inside your inside your blood vessel. Okay, you can contain it inside your blood vessel. Okay. Okay, having a wavelength at which the optical absorption for efficient blood is independent of oxygenation. So, okay, it is not not going to be affected by the oxygenation. So it is stable. So this is the assumption that the scientists, okay, that the researcher, the physicists, the engineers have to assume. Dia kena agak lah kan, supaya macam ni lah. Okay. Okay. Oops. Okay. So there's another one, thermodynamics. We use the cold saline. Daripada air garam. salt water, cold salt water. Okay, so 4 lumen catheter is floated through the branchial, okay, branchial vein into place in the pulmonary artery. So branchial mana? Okay, where is it? The upper limb lah kan. Okay, so the upper limb, this part lah. Okay, so there's a branchial vein. So I hope you can have a look okay, in the Google. Okay, please. Okay, if you don't understand, okay, some of the wording and so on, okay, please, okay, have a look in the Google. Because one thing, okay, as a university student, okay, you have to be independent. Okay, you have to be independent. Okay, I know sometimes, okay, we are complacent. Okay, we don't want to we don't want to be in okay, we don't want to be in trouble, bukan trouble lah, you tak suka susah. You want to make everything easy, so okay, you tend to like, okay, it is okay to ask everything to your lecturer lah. I mean, not okay lah, not that okay, but you need to be sometimes independent. Okay, unless if that's why I want to tell you a story lah. When okay, it's 41 already, tapi tak apalah, I want to tell a story lah. Okay, there are many things that, okay, maybe we can learn from, okay, how does the British do their job. Okay, I have this experience during when I did my masters. Okay, and it is they are very specialized, pengkhususan. If you learn, the word I like it during history lah, masa belajar sejarah, okay? During our form 4, okay, pengkhususan. What is the what is the thing that, okay, differentiate between a civil man and also mankind also, and also the prehistory and historical people and so on lah. Okay, this pengkhususan, specialization. Okay, I want to make it fast. Okay, but this is interesting. Okay, if the decision, okay, because when I did my masters, okay, I have usually all the decision, small decision, kecil-kecil, all the small decision, like for instance lah, kan, you want to submit your form lah, okay, your withdraw courses apa semua. This is have been what we call outline lah in the system, okay. So the what I call tani lah kan, the clerk, okay, the clerk can decide by themselves because it is already in the system. Okay, so during my masters, okay, I want to do actually my project lah, like you are going to do your FYP or IDP, okay, outside the university. I'm doing my masters in Keele University in the UK. Okay, so this is out of the decision of the management of the office. Okay, I mean that I know in our system we have AI, okay, or assistant registrar, is beyond. So at that time the dean will come and then she decide. Okay, Professor Alicia El-Haj, okay, she's still an academic in the university, Keele University. Okay, so at that time she decided, she comes down, she comes in, okay, she came in and then she decided, she asked why, okay, I want to do this, why I want to do a project in the Luton University and so on. I give an excuse lah. But then in the end of the day, the dean decide that, okay, because of the financial constraint and so on, maybe in terms of administration, okay, they create a project for me, okay, related to biosensor. Then finally I did my project because they don't have the project. Finally I did my project, okay, in house. Okay, so that's why I want to tell you one thing. Okay, if you have already in system, you know how like for instance, apa nama ni, for your IDP. For your IDP, you have like logbook, okay? Logbook. What are the things that should be in the logbook? Okay, it is routine job. It is routine work. It has been done for generations. I hope you can solve it lah. Kan? Tak payahlah tanya lecturer. Kan? If you have apa nama ni, you know how many survey kan to be done, okay, please find it from your lecturer lah kan. So there are things that, okay, you have to decide. Okay, unless if it is very administrative, then tak apa. Okay, very you cannot solve. Okay, but if it is like apa nama ni, sapu sampah pun nak suruh saya, susah lah. Jadi please, okay, be independent sikit lah. Okay, okay, so okay, coming back lah to more devolution kan, problems that could occur. Okay, possibilities of inadequate mixing between injection. Okay, because okay, these are the things that may induce a problem lah. Okay, possibility of inadequate mixing between the injection and sample site. Okay, there may be an exchange of heat between the blood and the walls of the heart. Okay, heat change through catheter walls with before and during and after injection. So these are the problems that could occur lah. Okay, so we have another 10 more. Okay, I hope we can. Okay, so now we have another another way of measuring the blood flow. Now we are going to manipulate the electromagnetics of the blood. Okay, so measure instantaneous pulsatile flow of blood. So it is based on the principle of electromagnetic induction. Okay, so the electromagnetic field induced in conductor. Okay, what is a conductor? So you have already your apa nama ni? You have already your notes kan, lecture notes. So please, please refer to this diagram. It's small diagram, but it's a powerful diagram. Okay, induced in the conductor moving in a magnetic field is proportional to the velocity of the conductor. Okay, so you have the magnetic field here. You can see the magnetic field. Okay, so it should be proportional to the velocity of the conductor. And then you have the permanent magnet positioned around the blood vessel. So it will generate a magnetic field, perpendicular to the direction of the blood flow. So it should be this is your blood flow. This is your magnetic field. Okay. So the voltage induced in the moving blood column is measured with stationary electrodes. Okay, you have the electrodes here. You have the electrodes. Okay, located on the opposite sides of the blood vessel and perpendicular to the direction of the magnetic field. I'm sorry, the ejaan is not complete here, but it's actually a magnetic field. Okay. So okay, this is the diagram. It's simple lah. Okay. So this is the equation. Okay. The magnetic field is B. Okay. This is the air, the length. Okay, the length may be from the electrode. Okay. The electrode length. Okay. And then the U is the velocity lah. Okay. So it is governed by this equation. Okay. When blood flows in the vessel with velocity U, okay, and passes through the magnetic field B, the induced EMF is measured at the electrode shown. Okay. When an AC magnetic field is used, any flux lines cutting the shaded loop induced and undesired transport voltage. So this is for the AC magnetic field. Okay. So this is different. So okay, like I told you, okay, if we have another test, okay, and I have to give my question, okay, maybe this is one of the favorite question that I will ask. It is between the what we call the differences, okay, the advantages and the disadvantages of using these two systems. One is a direct current DC flow meters, another one is AC current. Okay, flow meters. Okay, so okay, these are the things. Okay, by these two. But okay, the disadvantages of using flow meters, DC flow meters is that okay, maybe if you have a ECG, it can cause interference, and then the poor signal to noise ratio. So this may affect your reading. Okay. Design of flow transducer. Electromagnetic flow transducer is a tube of non-magnetic material to ensure that the magnetic flux does not bypass the flowing fluid and go into the walls of the tube. Okay, so you have the tube is made from conducting material. I hope you can, if you want to have more of the feeling, please have a, please go read. Okay, and insulated to prevent short circuiting of the induced electromagnetic field. So the induced EMF is picked up the point electrodes, okay, usually made from stainless steel or platinum. Stainless steel is good, okay, it's a good electrode, okay, but then okay, platinum is much better actually. Platinum is much better. Okay, so this is the probe lah. The flow head contains a slot through which the intact vessel can be inserted to match. Okay, okay. So the toroidal cuff, okay. So this is the shape of it. Has two opposite wound windings. Okay, so it has the winding. Okay, on each half of the core. Okay, the magnetic flux thus leaves the top of both sides. Okay, flows down in the center of the cuff, enters the base of the toroid. Okay. And flows up to both of the sides. Okay, so this is how how does it look? Okay, how does it look? Okay, here. Okay, another one is that through thermal convection. Okay, thermal convection velocity sensors. 78. Okay, maintain. So how many of you? 88. Okay. So we have like 22. Ada yang dah masuk, but then itulah. Okay. Just bear with me another maybe, I hope not more than 5 minutes, 10 minutes lah. Okay. Okay, so this is the equation. Okay. This W, the heat dissipated, and then by the thermistor. Okay, delta T is the temperature, A is the constants. Okay, the constants. Okay, log U is the velocity. So, okay, velocity sensitive thermistor RU, okay, we look at the A here, okay, is exposed to the velocity stream. So this is the stream of the blood, okay. Temperature compensating thermistor RT, okay, is placed within the probe. Okay, this is the probe, this is the, okay, thermistor, okay. Okay, thermistor placed down, okay, placed down and upstream from RU. Heated or not heated by RU, thus indicating velocity direction. Okay, so it is sensitive to the velocity direction. Okay, thermistor exposed to and shielded from flow can also indicate velocity direction. So, okay, this is shielded. Okay, this is exposed. Okay, so this is the equation that again is a heat dissipated by the thermistor. Then is the difference between the temperature, okay. A is the constants, B, okay, and then you have a log of the V, log of the U velocity. Okay, so this is a non-invasive, okay, plethysmography that measure changes in blood volume. Okay, like I told you, it is non-invasive. Okay, changes of volume in extremities. Okay, on your lower limb, okay, maybe your upper limb. Okay. You have the chamber plethysmograph. Okay, so we have this chamber plethysmograph. Okay, the venous occlusion cuff is inflated. Okay, to it is okay to give you some idea. Okay, maybe you can imagine your blood pressure cuff apa semua lah. Okay, okay, so inflated up to 50 millimeter mercury. Okay, stopping the venous return. Okay. Arterial flow causes an increase in volume of the leg segment, which is chamber will measure. Okay, okay, this explains the purpose of the arterial occlusion cuff. Okay, so this is chamber, this is a volume. Okay, so we measure okay, using the system. Okay, no, tak banyak dah, dua page only. Okay, this page, okay. So this is how you get in terms of the apa nama ni, your what are the, this is how does it the measurement looks like. Okay, you have the calibration first. Okay, okay, and then you start to measure it. Okay, after the Venus occlusion cuff pressure is turned on. Okay, I hope you still remember this one. Okay, Venus occlusion cuff. Okay, starts. Okay, the initial volume versus time slope is caused by you have the arterial inflow. Okay, so the the blood, okay, for arterial will have the inflow. Okay, after the cuff is released, slowly release. Okay, slowly release. So you just imagine like your blood pressure lah. Okay, release. Okay, the segment volume rapidly returns to normal. Then it starts to go to normal. If a venous thrombosis block the veins, return to normal is slower. So this is rapid lah, kan? You just imagine the number of the stroke. Okay, volume is fast. Okay, very fast. Okay, this one is okay, slower. The slope is okay. This is the slope is more lah. Okay, compared to B. Okay, this is our final slide. Okay. So another one is to measure this. Okay, using the electrical impedance plethysmography. Okay, so in science, okay, in measurement, in engineering, we use a lot of assumption, but it's a clever assumption. Okay, it is based on observation. Okay, but we have some ruling. Okay, so that it is easy for us to measure. I know in the perfect world it is susah, but okay, but if we don't do this, tak dapat apa-apa lah. We don't have anything lah. Okay, so the expansion of the arteries is uniform. Okay, so you have to assume that okay, the arteries expansion is uniform. The resistivity of blood does not change. Okay, it is constant. It doesn't change. Okay, and the line of current are parallel to the arteries. Okay. If you don't assume this, yeah, so your measurement is wrong. Okay, so the ZB is the is the impedance. Okay, and the rho B is the resistivity of the blood. Okay, the L, okay, the limb, okay, sphenical limb L. Okay, okay, and then the cross-sectional area is the delta A. So okay, so how you want to get this? Okay, you want to measure the volume. It is governed by this lah. The resistivity of the blood. Okay, your sphenical limb length. Okay, the electric impedance. Okay, then your electrical impedance here lah. Okay, so okay, thank you very much. I think that's all. Okay, so I will upload your async video. Okay, I hope before next week lah, before our session with Shamila lah. Okay, so my part, okay, actually we have it for my part. So that's all. Saya nak turn off our recording. Okay,